Hello everyone, this is the project of Mechanical Sessional Lab. I'm Asish Pani and along with me my team members are Harshada, Vinay, Anavkar and Gawande. So today I'm going to present the simulation of question number 6 of sheet 2, that is the wiper mechanism shown here. So let's start with the simulation. So this is the MATLAB code we have prepared for the simulation of the wiper mechanism. So this MATLAB code provides the simulation of the motion of the windscreen wiper mechanism, illustrating the complex kinematics involved in its operation. The mechanism consists of multiple interconnected links represented the wiper arms with their lengths and angular positions determining the overall motion. Now let's get deeper into the code. First of all, let me explain the key parameters used in this code. The scale is the scaling factor applied to the length of the wiper mechanism links. Now, L1, L2, L3, L4, L5. These are the lengths of different links in the wiper mechanism used here. So rotation denotes the number of rotations for the wiper movement, and there are various arrays to store angular positions of different links at different positions of time. Okay, so in this code, the lengths of wiper mechanisms are defined based on a scaling factor, and the link lengths are used to calculate the position of each link in the mechanism. So apart from link length, while calculating angular positions, the code calculates angular position based on the specified angular positions of link 2. These calculations involve trigonometric functions and geometric relations between the links. Now, coming to the third part, the wiping range calculation. So, the code determines the wiping range of the windscreen wiper considering constraints on link 5. The wiping range is calculated as the difference between the maximum and the minimum angular positions of link 5. So this is the final part of the code in which we have written the code for plotting and visualization of the wiper mechanism. First of all, for plotting the mechanism configurations, we have used the code that uses MATLAB plotting functions to visualize the configurations of the wiper mechanism at different points of times. We have shown the wiper arms, joints, and the wiping range in the Simulink, which will be shown in a few times. Apart from that, for the visualization of wiping area, like the wiping area is visualized by representing the plotting curve that outlines the motion range of the wiper blades. So now let's get into the Simulink of the wiper mechanism. This is the working Simulink of the windscreen wiper. As you can see, the area covered by wiping is also shown by the red dotted region. So let's move into the theory part of this windscreen wiper mechanism.
My name is Om Gawande and this is the synthesis model of question number 6 from tutorial number 2. As you can see in the given synthesis diagram, the area wiped by the windscreen wiper is shown and we have used the synthesis model to calculate the extreme angles of the windscreen wiper. For the arc length, we first got that theta equals to phi, which in turn is equal to phi dash, which is equal to 45 degrees, and the radius is 30 centimeter. So we found out the arc length by using the formula of theta by 360 into 2 pi r. So putting the value of theta equal to 45 degrees, we get the formula as 45 by 360 into 2 pi into 30 centimeter, which in turn is equals to 23.56 centimeter. For the calculation of the area, we use the formula of area as arc length into length of wiper blade. Using the value of arc length as 23.56 as calculated from above and length of the wiper blade as 20 cm, we found out that the area is 471.24 cm square. To calculate the area of wipe by the windscreen wiper, we have done the following calculations. Now let's move to the theory part of the windscreen wiper mechanism.
Hello everyone, my name is Harshada Anavkar, and let's move on to the Grishof's criterion. Grishof's law is a fundamental principle used to analyze the mobility of four-bar linkage systems. It helps determine whether a four-bar mechanism will result in a rotating motion of the revolute joint between the crank and the ground. The criterion states that for a four-bar linkage to have a degree of freedom, where one link can rotate freely with respect to its neighboring link, the following condition must be satisfied. S plus L must be less than or equal to P plus Q. S is the length of the shortest link, L is the length of the longest link, P and Q are the lengths of the other two links. If the sum of the lengths of the shortest and the longest links is less than or equal to the sum of the lengths of the other two links, then mechanism will exhibit a continuous rotation of one of its links, typically the crank or the ground link. The Grashoff's criterion is satisfied, resulting in rotating motion of the revolute joint between the crank and the ground. Moving on, the degree of freedom. The degree of freedom of a mechanism refers to the number of independent motions it can have. For a four-bar mechanism, the DOF can be determined using Grubler's equation, which is 3 into n minus 1 minus 2m, where n is the total number of links in the mechanism and m is the number of joints in the mechanism. For a typical 4-bar mechanism with 4 links and 4 revolute joints, the DOF is 1, indicating that there is one independent motion or parameter that can vary to describe the configuration of the mechanism. Next, the transmission angle. The transmission angle is a geometric parameter in a 4-bar mechanism that measures the angle between the coupler link and the driven link. It is essential in the design of mechanical linkages because it affects the efficiency and smoothness of a motion in mechanism. A larger transmission angle is generally preferred for the following reasons. Reduced angular velocity fluctuations. A larger transmission angle is associated with reduced angular velocity fluctuations in the coupler link, resulting in a more uniform motion. Improved mechanical efficiency. A mechanism with a larger transmission angle typically experiences fewer sudden changes in velocity, which can lead to smoother operation and improved mechanical efficiency.